We're going to look now at the halogenation of benzene. This is done by complexation with a weak Lewis acid, such as iron trichloride or iron tribromide. I'm going to use bromine. You also could use aluminum trichloride or tribromide. Iron tends to work a little better. But you're going to use these in the presence of the halogen. And the halogen would come, of course, in this diatomic state, Br2 or Cl2. And what's going to happen is they react to form a Lewis acid-Lewis base complex. Now the reason for this has to do with metal chemistry, of all things. So we're going to draw this like it's not ionic, but it's ionic. Now if you remember back from Gen Chem, whenever you have a metal and a nonmetal, they really do form an ionic complex. They're an ion pair. And I hope you remember that bromine always forms bromide, and each bromine would have a -1 charge, which means the iron in this case is a +3 in terms of its oxidation state. Whoops. It's a +3 in terms of its oxidation state. Now, as you remember, metals can have different oxidation states. There are several different stable oxidation states. If you remember iron, the most common would be a +2 or +3. It depends on what it's being paired up with. And so it can accept electrons or lose electrons. And what's going to happen is this iron is going to accept electrons. And as it accepts more electrons, we're going to change its oxidation state. And iron actually can be stable in many different oxidation states. So we're going to let it gain an electron in this process. And if you're gaining an electron, I hope that would let you know that you're going to a +2 oxidation state instead of a +3 oxidation state. We just do it a little different because we're organic chemists. But bromine literally is going to donate electrons to the iron. Okay? As this occurs, we form this Lewis acid-Lewis base complex. Now, the oxidation state of the iron here really is a +2. We aren't going to mention that. We're just going to say it's negative. That's because it's gained an electron. It gained the electron from the bromine. So we draw these as if they're covalent bonds. But be aware, metals and nonmetals don't particularly share well. Okay. But we are overall still charge neutral by doing this. Now, this complex is not stable, and it is going to break apart. But it won't break apart until it's in the vicinity of an aromatic ring. So we're going to have benzene. And again, remember, you can have electron donating or electron withdrawing groups on this ring. If you have electron donating, they will be orthoparadirectors. If they are electron withdrawing, they will be metadirectors. Now, as you can see with your Lewis acid base complex with the iron and the bromine is going to have a positive charge. There's a positive formal charge for one of these bromines, so it's electron deficient. And this is how we actually activate it and make it into the electrophile. One of the bromines is electron deficient. And the ring will act as a nucleophile to pick up bromine. So it will be an electron pair donor to a bromine. We don't pick up the one that has the positive charge, however. And as that occurs, we break this bromine-bromine bond, giving the electrons to the bromine that is electron deficient. By doing so, we make our favorite carbocation, our resonance stabilized carbocation, yet again. And as we've talked about on many occasions, this carbocation has resonance delocalization of the positive charge through the ring. So we will draw those. I'm not going to put in my electrons on my bromine. I hope you don't mind. And again, be aware that if you had a group already on the ring, especially if they were in the ortho or para positions, notice that the positive charge is on the carbon adjacent to these groups in the ring. So if they are electron donating groups, there would be a fourth resonance structure for this carbocation as it donates its lone pair into the ring. Or at least you would have inductive effects that would help stabilize the positive charge to a greater degree. If, on the other hand, the groups were meta, which I'm showing here in green, you only have these three resonance structures and you don't get any stabilization of the positive charge in the ring since that positive charge is not adjacent to those groups. We also have our anion at this point. Okay. Well, we still need to stabilize the charge and reintroduce the aromaticity. So I'm just going to draw out one of those resonance structures. And I will draw in the electrons again. And at this point, the iron-bromine bond will break, and it doesn't matter which of these iron-bromine bonds break, but bromine is the more electronegative of them. And so bromine takes those electrons, and as it's obtaining those electrons, it will come in here and remove the proton. As it is accepting the proton, this pair of electrons comes back and reintroduces the aromaticity into the ring, so that at the end, we've added the halogen to the ring. Note that this is extremely different from free radical bromination of alkyl groups. There's nothing similar about it, so be very careful as you're looking at conditions that you know what you're doing and when you're doing it. This is not like NBS. This is not like Br2 and UV light. If you want to get a bromine on the ring, you need to use a metal catalyst. You need to use the iron tribromide or the aluminum tribromide, or the chlorine versions if that is what you're choosing to use.